everyone. So we are back talking about polymers today. So I just want to give a brief kind of recap of the last video. So we started off by looking at our the first polymer that we've been investigating, which is, your first polymer, nylon 66. We kind of saw polystyrene as well. So remember, they're made of basically, actually we'll look at and create polyethylene, very common polymer. So remember, this is what? It is our structural unit because it is made of basically C double bond H. This is our monomer unit, also called our structural unit. For this type of polymer, we have one structural unit, one repeat unit. It repeats n times. We saw that n could vary from 10 to 100K. We see that most polymers are composed of those, all polymers are composed of monomers, but most monomers are composed of hydrocarbon chains, so saturated. So we are dealing typically, you'll see a carbon that is surrounded by 4 hydrogens, or something of the like. So they're completely saturated bonds. What's the bond angle here? And what type of bonding is this? So if we have CH4, if you remember back to materials in chemistry, that's an sp3 hybrid bond. We're dealing with tetrahedral angle. Tetrahedral. You know my spelling. What's the tetrahedral? What is the tetrahedral angle for that bond? Bond angle of a tetrahedron. It is. I could hear you all saying it in unison. 109.5 approximately. You could also have molecules like, let's see, just some reminder, BF3. That is trigonal planar. That angle is going to be approximately 120, exactly 120 degrees. And so that would be, if you remember back again from material science, sp2 bonding. And you could also have CaCl2 or carbon monoxide. There's lots of different kind of interactions like this. That bond angle is just going to be 180, and that is just sp bonding. So just a little bit. Probably you definitely didn't need to know that, but just a little good fun thing that you could have to show off. So we talked about kind of monomers, polymers, different bonds, hydrocarbon chains. We looked at kind of some examples here. Again, really important to know that big changes in orders of magnitude changes. So your degree of polymerization, or like the number of monomers, N, can vary again from between 10 to 100K. So you're dealing with 4 or 5 order of magnitude changes. That's going to dramatically change essentially the properties of that polymer in comparison to the other polymers. So lots of, the fun part about polymers and material science and soft matter in general is that there's lots of tunable parameters that you could play with in order to kind of design your system of interest. We also saw some functional groups. We kind of got into polar groups, things to watch out for. These kind of side groups will really dramatically change your intermolecular interactions, which we're going to finally talk about today, and determine a lot of different properties in your polymer. We also looked at kind of some general polymers that you might see, the different structures. Let's go back to our presentation. So if you zoom in here, you can kind of see, again, when you have these kind of these phenyl groups, these types of aromatic rings, so lots of carbons double bonded to each other. This makes this polymer extremely rigid along its backbone. Other polymers like polyethylene, you can see here, those are just single bonds. We're going to talk about in the next video isomeric states and rotations around those single bonds. So this polymer, polyethylene, is going to be a lot more flexible. So it's going to, again, dramatically change the properties of that material. Also, when you look along these polymers, be aware, again, look for those kind of polar groups, or kind of these possibilities, and we're going to see it again today, for hydrogen bonding. So amide groups, anytime you see N's and O's here, you could have essentially hydrogen bonding occurring. If you see any Cl's, nitrogens, again, they're going to cause those basically intermolecular interactions between polymer chains. That's going to make those polymer chains a little bit more rigid, change the mechanical properties. So be aware of kind of what happens there. And again, that's going to affect your TG. I'm giving a lot of information here. It's all going to kind of make sense at the end of this course. And it's unfortunately to kind of really, I can't help myself but explain as we go through and look at these polymers, how it affects essentially the material property. But don't worry too much. But the big thing is, again, so that backbone structure can change essentially what we talked about last time, which was architecture and then conformation. So if you have kind of these rigid backbone structures, your polymer is much more likely to become a linear or an extended chain. It will not, it will kind of be less likely to be branched or kind of these, random coil cross-link networks. So that's one kind of thing that you could already start to kind of think about and keep that in your mind. Same thing with configurations or conformations of polymers. So if you have a rigid backbone, you're less likely to become this kind of random coils. If you're flexible like polyethylene, random coil is definitely in your wheelhouse. But if you're like Kevlar or kind of these, if you have a lot of these kind of structures on your backbone here, lots of carbons, lots of double bonds, they're not going to want to rotate. You'll more likely be this extended polymer chain. And if you have kind of interactions, it could lead to kind of these helical formations or lamella. So again, there's lots of different types of conformations. Again, it's the beauty of polymers. It all depends on kind of just looking at that kind of hierarchical structure. So that backbone chemistry, again, we're not chemists. We kind of need to know a little bit, or like kind of how to play around with that. And then we finished up last time with talking about the kind of basic classes and classes of polymers: thermoplastics, thermosets, elastomers. So remember the thermoplastics, we could soften, we could heat them up, form them, cool them down, and then heat them up and do that, reversibly. So thermoplastics will go through, if they're semi-crystalline, that's a big caveat. So if your thermoplastic is semi-crystalline, it will go through a melting temperature, a TM. So if you're semi-crystalline, we have a TM here, a melting temperature. And again, we're not breaking the intramolecular interactions, which we're going to see today. We're not breaking covalent bonds when we melt polymers. We break the intermolecular bonds. So those are kind of the van der Waals interactions, hydrogen bonds, kind of those things. The reason, so when you actually, if you put a piece of polymer in a fireplace and you smell that kind of plastic burnt smell, that's denaturing the polymer. That's when you're breaking those bonds. So thermoplastics, as long as they're crystalline, they can have a TM. Amorphous polymers do not have a melting temperature, but they do have that TG, the glass transition temperature. And every polymer has a TG. So thermosets, elastomers, all of them have TGs. Thermosets, no TM. Why no melting temperature? Because again, it's this epoxy, right? You cure it, you set it, it's chemically cross-linked. You cannot essentially break those kind of chemical crosslinks unless you denature. So we're not going to undergo through a TM here. Same thing with elastomers, generally speaking. So that's what you kind of want to be aware of as we kind of go and talk more about this. So read up on those. Again, we're going to work primarily in this course, thermoplastics. Thermosets are fun. We'll look at them and look at them in the DSC specifically. And elastomers, I love elastomers, but that's kind of a whole class unto itself. I'll provide some of my lecture notes that cover elastomeric and gels, but we could kind of talk about that offline, or everything online now. So we'll talk about it online, offline at some point, and then we could kind of discuss if you guys want to do, if anyone wants to do a project based on that. And remember the big difference between thermosets and elastomers. Thermosets, heavily cross-linked, so 10 to 50%. Elastomers, less cross-linked, and then they could be pulled and extend. They're elastic, so kind of rubbery. So that's kind of just the overview of what we went through last time. I like to kind of do that before we get into the new material. But now we're going to get into the fun stuff, a little bit of chemistry, and then more chemistry on lecture 2, and then we'll forget about chemistry for a little bit while, except for chi parameters and other kind of fun things. But today we're going to talk about bonding and in that backbone, and kind of identifying, looking deeper into that structure and what makes polymers and soft matter so unique. And the key thing here is that polymers have intra and intermolecular interactions. So that's kind of the key, insight. So metals, you always have kind of these intramolecular interactions. So metals, ceramics, your kind of traditional materials, those always have intra. But polymers and soft matter are unique because they have intermolecular interactions. Because we have multiple polymer chains kind of always, intertwining like spaghetti, there's interactions essentially between like these polymer chains, not just the chemical crossings that we saw, but we're going to talk about kind of those intermolecular interactions as well. So that's kind of the key to these systems. So intra is within. So we still have intra interactions in polymer chains. That's just going to be kind of like your carbon-carbon backbone. So that is intra, within. Inter is between molecular interactions. So that could, again, be between chains or even kind of folded back like onto itself. So even in between its own chain. So these are what we're called secondary interactions, and they're much, much, much weaker. And actually, almost all of the intermolecular interactions are much weaker than the intramolecular interactions. The intermolecular interactions are usually on the order of 1 kT. Now, you may not have heard this unit before, or kind of this. When we talk about bonding, I'm going to kind of, in polymer physics, usually we put it in terms of energy, like how much energy is required to break that bond. My advisor, when I took this course, he kind of just said, these bonds are 1 kT and never really kind of explained what that is, which is a little bit hard to catch up with. But anyways, 1 kT, K is just your Boltzmann's constant. So Boltzmann, look that up. I believe it's 1.38 10 minus 23. Don't quote me on that. I'm going just off of gut instinct. So I believe that's Boltzmann's constant. There's also a value in EV. I think it is something like 8.6, 7, 10 minus 5. I'm going to check that really quick for you all. I know this is probably not fun listening to me, but I'm just interested in all right, I nailed the first one, so I still remember this, which is great for me. And I nailed the second one. Awesome. All right, good job, Josh. No notes required. I should add that to my notes. Note for next time. Remind me, students. Okay, so that is 1 kT. So kT, that's your Boltzmann's constants. When I say that interactions have an energy of 1 kT, I mean at room temperature. So T is just going to be your 298 K. So your intermolecular interactions typically will have an energy of 26 milli-electron volts to break that interaction. This is in stark contrast to your intramolecular interactions. So these are intra, which are generally 10 to 200 kT. So that is a big difference. So I've been talking about polymers are always fluctuating, they're moving around, they're these kind of really dynamic and adaptive, basically materials. How can we now rationalize why that's the case just by that value of 1 kT versus 200 kT? Well, let's think about it for a second, right? If I have thermal fluctuations, if my temperature is a little bit above room temperature, I have enough energy, or at room temperature, I have enough energy to break these intermolecular interactions. So these bonds at room temperature are continuously being formed, reformed, can be broken easily just by some thermal fluctuations. Here, intramolecular interactions, there's no, an order of magnitude change in temperature, we're in big trouble. We don't have to worry about breaking like bonds and other things, but so we cannot, those bonds are essentially fixed. They are not going to kind of move or fluctuate at all. So this is the key thing that makes polymers so amazing, beautiful, and frustrating, and hard to kind of work with because they're so adaptive. So even though they're weak, and this is kind of what I was bringing up last time in our video, is that more and more in biology, we're learning that these critical interactions, for example, for protein folding, for so many of these like critical biological processes, blood clotting, gave the example of von Willebrand factor. These interactions, these processes are governed by these weak intermolecular interactions because, for protein folding, this needs to occur quickly. We need to be able to go boom or open up like a gate in a cell, rapidly. So even on your lipid bilayer, it's these weak interactions that are fast and adaptive and dynamic that are kind of leading to these kind of cool properties. And we'll talk more later. Even a lot of these interactions, while they may seem small, think about it. So we're going to show a little bit later. So let's just say, we'll kind of name these. There's van der Waals interactions. Hopefully you've run into these before. So polyethylene may seem like a really boring, I love polyethylene though. Why? Because it's easy to draw. That's the hint. But anyways, polyethylene is kind of like your trash bag material. It's kind of really ubiquitous throughout material. So when you look at this backbone, this is flexible. Like what's unique about this? There's no polar interactions, but between each of these, we have van der Waals interactions. And again, they're small. They're 1 kT or probably even less. But think about this, right? In one, actually, this? I want to give the impression that it's not polyethylene. This is my polyethylene molecule. So these are small interactions, or weak, relatively weak, right? So we might think we don't care about those, but think about this. Remember, X or N, you'll see X as well. X can go up to 100K. So now you have one KT interaction that's multiplied 100,000 times. And that's just for a single polymer chain. Usually, again, in your material, in your trash bag, unfortunately, it's not just one polymer chain. You're dealing with millions of polymers. So these, again, it's all about the scaling, right? These weak interactions scale dramatically. So that is where kind of the strength, these kind of unique mechanical properties come from. And actually, we're going to talk a little bit about it later when we get into kind of the chemistry aspect of it, of polymerizing polymers. That's how you get Kevlar. Kevlar is a polymeric material. These weak interactions, relatively, these intermolecular interactions, they scale and they can create, a basically bulletproof vest. So that's where, polymers are so, again, so much fun. Let's do a quick review on intramolecular forces. Hopefully this should be a review from Engineering 45 or chemistry, but obviously it all comes down to your electrons. So valence electrons specifically. So that's going to kind of always determine your binding, whether you're giving up, sharing, and we want to know what's happening to those valence electrons. Are we sharing them? Are we taking one away? Are we, is it a sea of electrons where we're delocalized? That's what we're going to kind of figure out what bonding we're dealing with. So this is obviously if you haven't seen materials tetrahedron, whoever taught Engineering 45, shame on it, but this is the kind of the unifying figure of material science. I love this figure. It's on my, I think, YouTube video or my little icon. Anyways, so bonding is all determined by those valence electrons. And then again, whether they're being shared or whether they're being taken away or they're delocalized. So we are in intramolecular interactions. Typically, you're going to deal with these guys, covalent, ionic, metallic. And we're going to distinguish when each of these occur. Now, for polymers, you're almost always going to be dealing with covalent interactions. So again, these are just general energies. Obviously, there's lots of interactions like ceramics where they're ionic, but they can be stronger than covalent. These are just general ranges. The important thing to note, all of these are obviously well above 1 kT. So these are intramolecular interactions. So one quick question, why do we want to bond? Why do atoms want to bond to begin with? It's all about Gibbs. I told you, you're gonna be sick of hearing about this guy. So why do atoms want to bond? So let's ignore kind of the entropy aspect of it to begin with. Atoms want to bond because our enthalpy, which is basically, you kind of say this is your delta U. It's not thermodynamics. You're going to cringe right now at this video and yell at me. But basically, your enthalpy is your internal energy. So atoms want to bond because we want to, again, where do we want to go with delta G? We always want to make it negative. So we want to decrease our internal energy. And we can do that by bonding. That's the whole purpose. Bonding, taking two atoms like this, if these two atoms are apart, there's a lower energy state. And that's when our electron clouds overlap and we're happy. So atoms want to be at this kind of equilibrium distance. They don't want to be here because there's really no interaction. So basically your delta H, we're going to see, is basically almost zero. And then if they're too close together, again, I miss being in teaching because I could be really close and then make a student uncomfortable and show them that atoms don't want to be two together and then they want to push apart because, again, those electron clouds are going to overlap. So this energy is actually super, super high and positive. That is not good. So that's kind of the whole purpose of why do we want to bond to begin with. And there's, again, some potential energy from physics. We know that force is the negative gradient of internal energy. And there's lots of different potentials that show or figure out what is this equilibrium distance. So one of the most famous, there's tons that we could look into, but one of the most famous that you've hopefully seen previously is the Leonard-Jones potential. Really, really simple, really computationally effective and fast. People love using this for simulations because it's just, again, look at, there's so few parameters in here that you have to, really worry about and deal with. All you need is this epsilon fitting parameter and this sigma, and then that's it. So you plot your Leonard-Jones potential. So let's do, I'm going to do energy of my Leonard-Jones here as a function of distance. So as we said, the distance between your particles, so that is, or between your atoms, that's r. So at large distances, this is effectively almost zero. As we get closer to our equilibrium distance, we get negative, which is fantastic. But then if we get a little bit too close, we start to spike up there. That's kind of the shape of this curve and what you can expect. So epsilon is basically related to this, like the depth of the potential. So the depth of the well. This distance here is going to be your R naught. So like your equilibrium distance, or RM, basically. So R equilibrium. So that is your Leonard-Jones potential there. And then you could also figure out where is your force maximized as well from that derivation. That will be a PSET problem. So that's kind of, again, just trying to find what's this equilibrium distance. It's a nice, simple equation to run in simulation. So you'll see the Leonard-Jones potential pop up. And again, it's just talking about, again, get used to this energy. Positive energy, bad. We don't want to be here. Negative energy, this is where we want to sit at in terms of our energy landscapes. So how do we know when we have either covalent, ionic, or metallic interactions? Well, metallic, I'll keep it simple and easy for you. I'll skip right to the point. You need metals. So if you're looking at bonding between metals, so titanium, and have metallic bonding, and basically you have these kind of cores that are like positive. So positive cores of atoms in your kind of lattice, and you have kind of this just sea of kind of electrons. So this green is just all the electrons are delocalized. So delocalized, usually you're stuck in your electron orbits, but in metallic bonding, they're completely delocalized, and that leads to kind of your unique conductive properties. So that is pretty cool to think about. So that is metallic bonding in a nutshell. Covalent bonding is when we're sharing essentially these valence electrons. So they're sharing them between orbitals. Now the question is, are they equally shared, exactly, or are we going to get some where we pull more electrons, or we pull less electrons? So the whole idea behind it is we need to look at a material's electronegativity. So you can find that on charts online. You could look at it in periodic table and kind of estimate it depending on it. But this is kind of what we're really going to be looking at to distinguish between when we're covalent and when we are ionic. So on ionic interactions, we're grabbing all the electrons. We're grabbing everything away from each other. So if one atom grabs all the electrons, one gives it away almost entirely, that's almost a purely ionic interaction. So the question is, obviously, if I have carbon and carbon bonding, that's a pure covalent bond. If I have NaCl, that's pretty close to as pure of an ionic bonding interaction as you can get. But what happens in kind of these intermediate cases where there's not a huge electronegativity difference in between? This is where, again, things are frustrating because there's no unified standard. So the real answer is we're never really in this situation where we're pure covalent, pure ionic. We're usually kind of partially, either we call it polar covalent. So HCl is a good example of this. So there's no universally agreed kind of cutoff values, but in this class, if the electronegativity difference between two molecules or two atoms, so if the difference between this electronegativity is between 0 and 0.4, we're going to call this non-polar covalent, basically almost purely covalent. If it's between 0.5 and 0.17, polar covalent, greater than 1.7, we're going to call that ionic. So that's just kind of the cutoff. This is taken from a book by Sam Allen, The Structure of Materials. I have a lot of fun Sam Allen stories. Unfortunately, we don't have Friday classes, so you don't get to hear Sam Allen joke day. So you have to take my Engineering 45 class to experience that. But that's kind of how we're going to deal with intramolecular interactions. So metallic, covalent, ionic. Typically, for polymers, we're only going to be dealing with covalent. So now we're into the fun ones, intermolecular forces. So for intermolecular forces, we have a lot at our disposal to kind of look at, investigate, and work with. First, there's kind of these, we've kind of looked a little bit about van der Waals interactions. So van der Waals is kind of like a general term for kind of, again, these like really weak, they include the London dispersion force, Debye force. They're very, very weak interactions that's due to fluctuating polarization between nearby atoms, elements. Basically, van der Waals forces is, when you look at even just your C and H, and there's other, polymers or different structures in your backbone that could be, that could be occurring here. There's always going to be kind of like these other surrounding elements that want to kind of pull or grab. The electrons are kind of always in flux. They're around your orbit, but sometimes they can fluctuate where they're more towards here, and then it creates this kind of dipole, right? So where one charge is, slightly positive, and then one charge or one atom is kind of slightly negative. And that leads essentially to, this kind of fluctuations, rarely really short-term fluctuations, but then we have to go and look at these short-term fluctuations can cause essentially these van der Waals forces to appear. And actually, it's really important to see they decay as d to the minus 6. This is critically important. Intermolecular interactions, almost universally, they get stronger as you pack them tighter and tighter and tighter together. So as my chains become tighter and tighter and tighter, just like Kevlar, these interactions increase, intermolecular interactions. So that's, again, a key point to how we, that is a critical point in terms of how we basically process materials. So that's what we want to kind of keep going forward. Hard sphere potentials, again, repelling at short distances. This also is kind of, you can think of this as steric hindrance. So there's some interactions between particles. We don't want to kind of occupy each other's space. So they could kind of repel each other. They could kind of, again, they're still interacting. Coulombic electrostatic interactions, these are really kind of strong in terms of the intermolecular interactions you might deal with, and they're between charged ions here. So that is kind of the key aspect that we want to. So if you see any positive or negative charges along your backbone of your polymer chain, that should ring some really alarm bells here. So you want to kind of deal with those. Leonard-Jones potential are kind of, again, these induced dipoles, very similar, a little bit, again, chemists will hate me, but similar to your van der Waals forces interactions. Dipole-dipole interactions, these are polar molecules and forces. So again, if you see chlorine, fluorine, nitrogen, oxygen, electronegative elements, the red flags again go up. These are going to kind of cause these intermolecular interactions to occur basically along your polymer chains. Hydrogen bonding, hopefully you remember these. Again, these amide linkages. Let's see if I can draw it from memory. See, I'm a chemist. I need a chemistry degree. But anyways, you can have hydrogen bonding in between here. So you've probably seen this more with our beautiful oxygen or water molecule, not oxygen, where you have this negative dipole because this wants to grab the electrons, this wants to give away electrons. So you had this kind of net dipole effect, and that can lead to hydrogen bonding as well. And then hydrophobic effect. Again, if there's some molecules are hydrophobic, hydrophilic, that could also lead to some interactions. Then finally, ionic bonding. So sometimes you could have metallic ions actually on your side chains. That was my doorbell that just rang. Remote teaching, you can't. I don't have the soundproof. Anyways, ionic bonding basically can occur between if you have some metallic ions, that could contribute as well. So these, in my opinion, this guy, these, and these can have some really, really strong effects. I should have, sorry. Let me undo. I'm going to do color. So, even though you're following along the video, I know. These are the ones you really need to watch out for. And when I mean watch out for, I mean these can really change our, these are kind of our tools in terms of designing our materials that can really have an immediate impact on the properties of our materials. Van der Waals too. Van der Waals are amazing forces. It's actually why geckos are able to kind of stick on walls. You examine the structure of a gecko pad, and there's this hierarchical structure where there's tons of van der Waals interactions, and that's what allows them to stick onto your wall. So all of these can contribute depending on, again, the number of polymers, the structure. And again, that's why polymers are so fun to study, but also so difficult, because there's all this kind of common, opposing effects, contributing effects, and we have to kind of distill down the entire picture. So, yeah, so that's inter and intramolecular interaction and intermolecular bonding in a nutshell. So next time we're going to talk about isomeric states, have a fun but also kind of a little more serious talk with thalidomide next time. And yeah, then we'll be finished with lecture 1. So thanks. And I'll see you all next time. Let me know if you have any questions, and bye.